Hi everyone, welcome to this talk. So I've been working in and around scaling laws for a year or so now, and in this video I'm going to kind of give a compressed background to some of the kind of prerequisite knowledge for understanding what scaling laws are about. And I'm also going to kind of briefly introduce a couple of the recent papers that I've been involved with. So yeah, plan for today, a very brief history of scaling at a high level, and then some more detailed background on some prerequisite knowledge to understand scaling laws specifically. I'm going to talk briefly about a project I was involved in around scaling optimally in LLMs, and finally touch on a project scaling optimally in embodied AI. So if we kind of rerun the clock a little bit, back to sort of mid 2010s. Already at that point, I think there was quite a clear realization that bigger models were better. This table is from 2015 image from the ResNet paper, and they find that increasing model size, increasing the number of layers specifically, going from 34 to like 152, reduces your error on ImageNet. And I remember at the time I was just kind of entering the AI research field, and I remember looking at this and thinking, wow, this is kind of an obvious and somewhat boring result. Obviously a larger neural network, can model a more complicated function. So it should be able to score like a lower error. And yeah, to me it felt like, this is kind of obvious. Like let's focus on the interesting thing, which are like algorithmic improvements, architectures, learning algorithms. And I think from that point that there was then a sort of gradual refinement in the way the community started thinking about scaling. So there was this paper later on in the 2010s that started thinking a little bit more scientifically, I would say, about how best to scale your model. So they kind of observed that there are different ways you could scale the model. So you could do the thing that we just saw of depth scaling, adding more layers. But there were also other papers that started to, for example, introduce width scaling and saying actually making these networks wider also works very well. And you could equally also add more channels to your, at this time, these were CNNs. And so what this paper did is they start doing some kind of empirical ablations, and they find that actually doing a mix of these things is what ends up being most effective. So kind of scaling these different dimensions at some rate. And so on the plot here, we have the amount of test time compute on the x-axis and the accuracy on ImageNet on the y-axis. And I think this is something we're going to see change in a second. So at this point, ImageNet felt like a very big data set, but in many ways we were still sort of data set size bottlenecked. And so in some ways, the amount of training compute you poured into these systems, in some ways didn't matter so much. It was more about, well, anyway, we're limited by the amount of data. So it made sense to care more about like how fast these things are at test time, or how much compute are these using at test time. But I think this started to change. So then around kind of early 2020s, I think there was a very important shift in mindset. So we started to see more work on language models coming out. And there's this very sort of seminal paper at this point that came out in 2020. And on the left-hand figure here, we see something that is maybe similar to the ResNet days, where we're training models along the x-axis, and we're finding that as we increase model size, we add more parameters. The test loss goes down, which is not hugely surprising. But what they do is they sort of have this mindset shift of like, okay, rather than maybe the thing we care about for language models is actually the training compute. So moving to language, right, you suddenly have like a much larger data set than we had access to before. And we like a lot of the pre-training that gets done on these systems are not really using much more than like one or two epochs on the data. And so if you if you transform your x-axis to be in terms of training compute, then you start to see something that looks a bit different, where you don't strictly get that a bigger model is always better, and actually, at higher values of training compute, larger models are better, but actually at smaller values, maybe smaller models are going to give you a lower loss. And I'm going to dig a little bit more later on into exactly how we calculate training compute. But at a high level, we have this equation of C equals 6 times N times D. And yeah, to start giving some intuition about this, this is essentially saying that model parameters and data set size are, you can directly trade one off with the other for a given amount of compute. So for some value of C, you could have like a large N and a small d, or a small N and a large d. And these would give you the same value of C. One kind of really useful insight from this type of analysis is that it starts to give you a way to think about how to size your models in the best way for a given compute budget. And again, this is something I'll come back to in a little bit more detail later. But essentially, we can end up with these types of plots where we have, say, the amount of training compute on the x-axis and what is the optimal size of the model on the y-axis. And we can fit this to some models at small scale, and then we can extrapolate this out, and this gives us an estimate of the optimal model size for our kind of final big training run. And I think at this point I was kind of watching this stuff happen from afar while I was focused on some other parts of AI research. But at this point I started to kind of have this realization that actually, a lot of the progress that was being made in AI was really coming from this scaling up process. And in some ways, focusing on these algorithmic improvements, maybe started to feel like less of an important thing compared to really starting to understand this scaling process. And so I kind of began to shift my research a little bit more towards focusing on understanding scaling up. Okay, so that's kind of a brief history, as I see it at least, of how these kind of scaling trends have evolved. I'm now going to talk a little bit about some more concrete background. So for a start, I want to just say very simply, like, what is a scaling law? So this is beyond like just AI. A scaling law is any relationship described by a power law. So you have some x and y variables, and this is your power law. We often see these things transformed to log-log axes, where you then basically see a linear relationship. And so, why do we call this thing a scaling law? Actually, like, if you dig into this a little bit, you'll find that people say that this comes from the idea of this power law being scale invariant. And so, specifically here, what we mean is it doesn't matter the magnitude of x. If we doubled x, y would always double by the same amount of like 2 to the power of b. So we're timesing x by 2, and y always increases by 2 to the b. And this sort of holds over many orders of magnitudes. And maybe more intuitively, like, I think when you first look at this equation, it seems super simple, right? It's just 2 parameters. But actually, if you think about the types of functions that we like often encounter, there's quite a broad range of things that are captured by this. And especially when you start to relax this a little more. So, sometimes people are adding in offsets into scaling laws, and they can even like add different components together, either like multiplying or adding or summing together. So yeah, there's actually quite a wide space of functions that these power laws, with a bit of flexing, can capture. And so where do these appear? Actually, as I mentioned, this is much bigger than just AI or neural networks. So scaling laws are a pretty like well accepted idea throughout the engineering and sciences. So I put a couple of examples here. On the left, we have we're predicting this size of the crater, say on the moon or something like that. And so X is going to be the diameter of the thing hitting the planet, and then Y is the diameter of the crater. In biology, we see these things pop up in different places as well. Maybe a little bit of interest to AI people is, for example, you get these relationships between body mass and brain mass, and this, at least for certain like classes of animals, certain types of species, you get these like nice power laws as well that hold over many orders of magnitude. And so when we talk about neural scaling laws, really we're just taking this idea of a power law and we're swapping the meanings of Y and X. So on the representing the X, we normally have either compute, model parameters, this model size, or data set size. And then on the Y-axis, usually we're thinking about loss, although sometimes you see papers that explore some other metrics. So maybe a specific benchmark, something like that. But I think loss tends to be the more common one that people are focusing on. These are some ideas that have been studied for a little while. So pre this sort of 2020 scaling laws paper. So back in 2017, 2019, there were a couple of nice papers that really start to realize that empirically, loss curves are actually quite predictable. But it was really the Kaplan et al. Paper that start to that I think really popularized this idea. They also started to popularize the use of scaling laws in this context. They're really showing that with these three dimensions: compute, data set size, and parameters, number of parameters, test loss goes down in a very reliable way. And of course, this is in itself, this is a really important observation, and this is something that's kind of guided a lot of labs to be willing to invest more and more compute and resources and funding into training bigger and bigger models, kind of having somewhat I can't say it's a guarantee that things will always get better, but at least there's precedent to say, well, so far things have always got better, and there's no obvious sign that they will stop getting better. Okay, so I'm going to talk a little bit more detail about a couple of aspects now. So one is around how we count compute. So this is something I touched on that I introduced very briefly earlier. So we have this equation, C equals 6 times n times d. And I want to give a bit of intuition as to where this comes from. So the first thing to focus on is what are we actually saying when we talk about compute? And really we're talking about flops. So this is floating point operations. So you have two floating point numbers and you do some operation to combine them. So this can either be an addition or a multiplication. This is one flop. So you take two numbers, add them together, this is one flop. Two numbers, multiply them together, this is one flop. In neural network world, normally what we're doing is matrix multiplications. So here, think about, we have, say, one data example of dimension d, and we're going to multiply it by a matrix of parameters of d by h. And so we end up with a 1 by h output vector. And so let's count up, okay, when we do this matrix multiplication, how many addition and how many multiplication operations are in this. If you think about this, for the first element in this output vector, we're multiplying this thing by all of these numbers, right? So this is going to be So we're going to have d of these like multiply operations, and then you have d minus 1 additional operations. So this is for one element, but then we want to do this for all h elements. And so we're going to have, so this is d plus d minus 1, so this is roughly like, 2d. And so to do the whole vector, we're going to have 2 times d times h. And yeah, if we replace the meaning of d times h and say, well, actually, this is just the number of parameters in your model, capital N. So then we'd have 2 times n. And we've done all this just for one data point, right? So then if we had capital D of these data points, one matrix operation would be 2 times n times d. So this is where 2 times n times d comes from. But why do we end up with 6? There's kind of one more step here, which is when we do a forward pass, it indeed only costs us 2 times n times d. But when we do the backward pass, we actually need to do 2 matrix multiplications, one to get the gradients on the parameter matrix, but then another time to kind of get the gradients on the vector in order to back propagate further back into our network. So hopefully we then get 1 plus 2, 3 times 2 to the nd, so we get 6 nd. So yeah, hopefully that gives a bit more intuition to where this formula is coming from. This is not a perfect formula, so I think there are 2 limitations. One is that this formula implies that every parameter in your neural network is sort of used for one matrix multiplication, and this is not always the case. So for example, when you have attention, there's going to be you have, say, the keys in one token stream will have to be multiplied by the queries like in all the other token streams in your sequence. And there's some kind of a reliance on sequence length for this, right? If you have a longer sequence, you're going to have to do more of these multipliers. But it turns out that most of the parameters at least in bigger transformers, really come from the fully connected layers, where this approximation, this 6nd, is actually pretty accurate. Second limitation here is ultimately, what you might care more about is as a researcher is how long is this thing going to take to train? And there are situations where flops might not always be proportional to GPU hours. So that's another caveat. Another really key equation, that I want to briefly introduce is given on this slide. I found this really helpful to kind of have at the front of my head when I'm doing a lot of scaling research. So this is predicting how the loss of a system decreases with the number of parameters and the amount of data. And then you have these new constants that we're introducing, and alpha and beta are also constants, as is E. And really we have, these 3 different terms in the equation. So starting from the right-hand side, you have this kind of, people could have different names for it, but some people call it fundamental entropy of language or something like this when it's being trained on language models. Essentially, this is capturing there are certain things in my data set that are just unpredictable. And so, for example, if you're doing language modeling, the very first token of your sequence, you don't have any context for it. So really the best you can ever do is guess according to the probabilities of the tokens in your data set. So there's always going to be some loss from that. And so this E is capturing sources like this. Then there's these 2 other terms. So the one on the left is basically the error that comes from having too simple of a model. So your model cannot really cannot really capture the true function in your data. And so you're going to have some error from that. As n goes to infinity, this bit goes to 0. But we're always at some finite model size where there's going to be some error induced by that. And then the middle piece here is I like to think of this as how many patterns has your model seen, and really it's there's some error from like not having seen enough patterns in your data to know exactly what's going to happen next. And if I and to demonstrate kind of the types of curves that this type of loss function produces, on the left-hand plot I've got some like synthetic training curves generated from this, and on the right-hand side I've got these these real curves from the Kaplan et al. Paper. And hopefully you can see that these are roughly capturing similar behavior, where at early values of compute, smaller models plateau earlier. Later on, the bigger models become preferable. It's definitely not perfect. So one thing I've found is that like the smaller models tend to plateau more quickly. So this is kind of a sharper angle here, whereas larger models sort of take longer to do that plateau. And I think this behavior is not particularly well captured in this equation. So this kind of assumes more of a similar rate of plateau between the different models. But still, I've found this a very useful equation to have, as I said, like in my head when doing a lot of this work. Okay, one more thing I think is really important from these analyses is something you can do with them, which is to predict the optimal number of parameters for a given amount of compute. So I mentioned this very briefly earlier on. If we start on let's think about how we would do this based on this kind of a plot on the left-hand side. So we've got this, our favorite training compute versus loss plot. And then maybe we can start to say, okay, given we have this specific amount of compute, what's the best model size? And so what does a best model size mean? This means what model size gives me the lowest loss for this amount of compute. So you draw the line up here. The first line you hit, you kind of look at the color of it, and then that's the optimal model size for this amount of compute. And so as you go to a bigger amount of compute, you hit now this more like yellow color line, which is going to be a bigger model. And so we could think about plotting this, right? So we could do this across the entire axis, and then we could plot this graph of training compute on the x-axis and the optimal number of parameters that we found on the y-axis. One thing I want to mention here is that, so I've talked about this for parameters. You could do a similar thing for data set size. In fact, if you subscribe to this 6ND equation, then one implies the other in the sense that these two optimal coefficients need to sum to 1. And so, a lot of the time you see papers, they will only really focus on one of these numbers, and the other one is sort of 1 minus the number that you found. A nice thing that you can do with the two equations I introduced, both this loss equation and this C equals 6ND, is you can actually combine these and with a bit of manipulation, you come out with these estimates that n optimal is proportional to this beta over alpha plus beta, where you take alpha and beta from this original equation, and d, the d optimal coefficient, is alpha over alpha plus beta. So again, these guys sum to 1, and it's kind of a nice result because it sort of implies that the final value of these coefficients you end up with really comes from the ratio between these alphas and betas. Cool. So I'm going to quickly introduce one paper I've worked on in this area, which kind of ties together with a lot of the things that we've spoken about already. So this was published in TMLR last year. This is joint work with my co-author Jinyop Song. So starting from this Kaplan et al. Paper, they did this analysis of how should you set your model size for a given value of compute, and they came up with this estimate that the optimal parameter coefficient was 0.73, and and this means that the data set is 0.27, which is much smaller, of course. And so, what does this mean? This means a bit more concretely, like if someone doubled your compute budget, you should spend by 2x. You should increase your model size by 1.7x, but you should only increase your data set size by 1.2x. And this really led them to conclude that, this quote, big models may be more important than big data. And at the time, so this is a figure taken from 2022. There was sort of this kind of this race to like train bigger and bigger models. And at least to my understanding of this, like a lot of this was driven by these kind of estimates that said, big models are more important. Maybe the data size doesn't matter as much. And you had a lot of labs that were training these models that were very large. And then a couple of years later, then in 2022, there was Hoffman et al. Basically redid this analysis, and they said, we're going to run our own experiments and we're going to come up with our own estimate for how model size and data set size should be set. And they ended up coming up with quite different estimates. So they said, actually, these coefficients are 0.5 and 0.5 around. So, what does this mean? This means like every time I double my model size, I should also be doubling my data set size. And so this kind of contradicted with what Kaplan et al. Had said. And really this started then a trend towards people training smaller models for longer, or more data, I should say. Now the explanation that they gave in the paper turns out to not be entirely correct. So I think part of it is right in that they talk about the model sizes in the two papers being quite different. Kaplan et al. Used smaller models, whereas Hoffman et al. Used much larger model sizes. But it actually turns out that there's quite a simple reason why this this original paper didn't quite pick up on. I got really interested in this question when I was reading this Hoffman et al. This Chinchilla paper. I was interested to start with which one of these is even correct. Is it the Chinchilla one or is it this Kaplan estimate? And why do they disagree? What's kind of nice is that in parallel with Ginyops and my work, there was another paper from Poirion et al. That also sought to answer like this same set of questions. And what's nice is I think we end up coming out with pretty similar conclusions, at least for the main source of the difference. We both agree that the Chinchilla estimates are correct, and really the reason for this difference is that Kaplan et al. Made a very specific decisions about how to count parameters that differed from Chinchilla, and this really is. I'll show a little bit about why this leads to these discrepancies. I think what was nice about these two papers as well is that we tried to take a slightly more analytical approach, where we really stuck to the information available in the two papers. But the Poirion et al. Paper, they run a lot of experiments empirically to verify these things. Okay, so what is this? What is the reason for this difference? As I mentioned, really it's in this choice of how Kaplan et al. Chose to count parameters. So they break down the total number of parameters into embedding and non-embedding parameters. And here embedding are kind of the first and final layers of your transformer. So this is like the residual stream, the model dimension of your transformer, times both the context length and the vocab size. So back then people were using a new position embedding for each token in your sequence. Actually what Kaplan does is they choose to only count non-embedding stuff. So they kind of say, well, maybe maybe this first and last layers are not that important, and you know, the interesting stuff is happening in the core of the model. And they both count up this in terms of parameters, and they also do that in terms of compute. So we have this concept of non-embedding compute, which is just going to be 6 times your non-embedding parameters times your d. And so really you can like start to write these two findings a little bit more accurately. So for Kaplan, this is non-embedding parameters proportional to non-embedding compute to the power of 0.73, and Chinchilla is total parameters proportional to total compute to the 0.5. Now, I'm not going to dig into the full detail of exactly why this causes the issue, but I do want to give a little bit of intuition as to what happens here. So at the core, if you plot the number of non-embedding parameters on the y-axis versus the number of total parameters on the x-axis, you get a graph that looks something like this, where at large model sizes, you know, the embedding parameters, your first and last layer, these are very small proportions of the total model size. So you end up with basically the y equals x line. But this is not the case at small model sizes. So because the experiments that Kaplan did were always using a fixed vocab size and context length, and the vocab size is maybe in the tens of thousands, you know, even if your model dimension is very small, you end up, you know, this NE, this embedding parameters ends up being quite large. And so and quite a large proportion of your total model size. And so at smaller model sizes, you know, you get this curvature away from the y equals x line. And, you know, in some ways, if Kaplan had done their analysis at very large model sizes, so say, you know, 1 billion parameters and above, this would not have mattered. The problem came that they do their analysis at relatively small sizes, so all the way from around, I think, a couple of thousand parameters up to 1 billion. And they're in this region where this curvature affects things quite drastically. And so in the paper, there's a few more steps you need to do to kind of close the loop to show that these coefficients are can be reconciled. But essentially, this is the, you know, what I want to present today is that this is the kind of core reason for this difference. Okay, and then I wanted to speak briefly about a second piece of work I've been involved with recently around scaling laws, where we've been looking at embodied AI settings. So we've really been thinking about, you know, can we take some of these ideas from LLMs, from what we understand about scale in these other settings, and can that be helpful in embodied AI? Something I want to quickly introduce here is like a little bit of background to what's going on in scaling in embodied AI. So I think even in the past couple of years, 2023, 2024, I've grabbed a couple of like really important papers in embodied AI. And I kind of looked at, like, you know, what were they doing when it came to scaling? And essentially they, you know, what a lot of people are doing is essentially training a couple of model sizes, smaller ones and bigger ones, and checking that the bigger models perform better. So over here, this axis is something like task success rate, and so the bigger models get score better than the smaller models. We have a world model paper here, where again video quality gets better with model size, and we even have with a kind of world model where you're training a policy in a Dyna style loop, and again bigger models perform better. But, you know, in a way, hopefully this might remind you of what I mentioned at the very start of this talk, which is, you know, we've kind of known for a long time that bigger is better, you know, back from 2015 ResNet days. And so I think something that I started to realize in embodied AI is that, you know, the practices that people are applying there compared to what people are doing in language modeling, there's a really big gap between these two things. And so in this paper, we analyze a couple of popular embodied AI tasks. One of world modeling, so where you're predicting the next observation given previous actions and observations, and behavioral cloning, where you're predicting the next action given previous observations. We had access to a very large data set of humans playing a video game. This game is called Bleeding Edge. We have both access to the videos of this and the controller actions that the humans took. I think this data set in some ways was pretty important for the analysis that we wanted to do, because we wanted to be in a data regime where we were not having to repeat training on the same portion of data many times. This is what we're doing in LLMs. We call it like the infinite data regime sometime. And there are not a huge amount of embodied AI data sets out there that really are big enough to do this, and even even less that are really open source. We also wanted to have an environment that was kind of complex enough, both in the world, in the observations that we were getting back, and also the behavior that things wouldn't very quickly saturate when we train very bigger models. We hope to see that as we put in bigger models and more data, things got better. And this is really exactly what we saw. So the first question that we had is do things improve as predictably in embodied AI as we've seen in language modeling? And so for both these tasks of world modeling and behavioral cloning, at least when you structure the model in the right way, you see very similar patterns to what we see in language, where, for a given amount of computing flops, smaller models sort of start being efficient and then plateau earlier. And then with higher compute budgets, larger models give you a lower loss. And really, this is the types of patterns that we've seen in language modeling. So in a way, this is like a really good piece of news for embodied AI, that things do seem to improve as predictably as we've seen in things like language. In some ways, this justifies, I think, putting more and more resources and more funding into these systems. There's an important detail, though, which is that particularly for something like robotics, we're much more constrained on the amount of data. So we don't have this kind of internet size scale data set waiting for us to just pour into our models. And so there's sort of a follow-up question to this, I think, which is, what does this mean for data generation? And does it mean that we should go all in on curating and creating data, or does it mean that we should be looking for more data efficient algorithms? Now, another thing we did in this paper, again, based on some of the things I've spoken about earlier, was we started looking at sizing models in an optimal way. And similar to language, we again found that we could plot these very reliable shapes where you have compute on the x-axis and optimal number of parameters or data set size on the y-axis, and you get these nice kind of clean power laws coming out. So thanks for listening. Hopefully that's been of some interest. As I say today, I tried to really give a quick bit of background into both some fundamentals, some prerequisites for understanding scaling laws, and give a little bit of a taste of some more kind of frontier research that I've personally been involved with. There's a lot of other great work on this area coming out still, though. So yeah, it's an exciting area to be involved with. Thanks for listening.